Ooh.
Phone ringing.
No. There is here. Yes.
We'll say the light. For number 2.
Okay, so for number 2 on page 48.
I circled NH2 minus and C6H5COOH. Wait, I think that was for number 3. Yeah. I circled NH2 minus and C6H5COOH minus. Well,
Hold on. That's not, number 2 doesn't ask you to circle anything. Number 3. G.
Yes.
Okay, circle all the amphiprotic substances given in questions 1 and 2. So you said you also circled which ones? This one?
2, that one, and then the C6H5COO minus.
C6H5COO minus. Okay, so they have negative charges. However, they do not have easily removable hydrogens. They have hydrogens, they're just not the right kind of hydrogens. Now, the NH2, the reason we know that is not amphiprotic is because if we look on our data booklet, it is a strong base. So it only accepts protons. If it's a strong base, it's going to be like it cannot act as an acid. Yeah?
So I didn't look at that.
Yeah. And then for the other one, this one here, we have C6H5. That's a benzene ring. C6H5, COOH would be the conjugate acid, yes? And the other H's are around like this. Okay, and then we have our alternating single, double, single, double, single, double. Do you guys remember benzene? Little bit? Okay, benzene is a 6-carbon ring where it alternates single, double, single, double, single, double. And so we would get resonance where these bonds like kind of move around. Yeah? This hydrogen can come off because it is right next to a very electronegative oxygen, and there's another electronegative oxygen right here. So those are pulling the hydrogens away from pulling the electrons away from the hydrogen. So the electrons in this bond here get pulled that way, and the hydrogen comes off and becomes H+, and it leaves those 2 electrons behind. Okay. Whereas these hydrogens are attached to carbon. Carbon has a very similar electronegativity to hydrogen. So there is no, like that bond is not polar. It doesn't, like the hydrogen is not lacking electrons. The electrons aren't being pulled away from it. So none of the other hydrogens will fall off. Okay, so when you have an organic acid, anything like if you have CH3, COOH, only this one is an acidic hydrogen. None of the ones on the carbons. Okay? Yep. Anything else? Yes. 6C. Okay, so complete the following reactions. It's possible I did it wrong, so let's check this out. We have HPO42 minus and AC6H5O7. Okay, so we have HPO4. Which is here. And we have HC6H5O7, which is there. So that means out of those two amphiprotic substances, the monohydrogen citrate ion is stronger. Yes. If you have two amphiprotic substances, right? Because they are both amphiprotic. One of them is going to be the acid. One of them is going to be the base. So if you have two amphiprotic, then before the products are predicted, you have to say which will act as the acid and which will act as the base. Does that make sense? Cool, cool.
That's how you know like which one gets the H and which one.
Yeah, exactly. It's not that they won't do it the other way sometimes, but the predominant reaction will be this guy donating and this guy accepting. Yeah, so the stronger acid will act as the acid, the weaker acid will act as the base. Yes. Yes. Good question. You will get one like that on your quiz on Thursday. Two amphiprotic substances together. Yes. 6I, yes, for sure. Did you want me to do that one, Justin, or are you good at this point? You're good at this point? Okay, perfect. 6I. Okay, so we have NH2, which is a strong base. Okay, we go back here and we say, oh, where's NH2? There it is right there, strong base.
Wait, so like you have these counts. I was looking on this question, and I'm trying to find like on the contrary side, like I found HCO2 minus, like this minus H2 minus it's on the other side.
So if it's a strong base, the stronger the base, the weaker the acid. So if you are a strong base, you're going to be too weak to be an acid. Because it's going to grab every hydrogen it can. So would it give up hydrogens? No. Right? It's going to grab an extra hydrogen. It's certainly not going to give away another one and become NH2 minus. There's a fly in here. That's irritating. Oh, well. Okay, so NH2 is a strong base. HCO3 is amphiprotic. But because it is working with a strong base, HCO3 minus must act as the acid. So it's going to be the acid. So we will end up with then NH3 plus CO3 2 minus, and I have made a mistake already. What mistake have I made?
State
Hold on, I couldn't hear any of you.
goes to completion.
Goes to completion, yes it does, because if you've got a strong base, it will rip all the hydrogens off of whatever it is, okay? And I didn't write the state, so this will be aqueous and this will be aqueous. And then did it ask us to predict? Oh, well, in this case, because NH2 is a strong base, this goes to completion, so the KEQ would be very large. And it completely favors the product. It just goes to completion. Demi. 6G. Okay, so we have HSO3 and H2PO4. Once again, what? Oh, the charges are wrong. Yes, I have a tendency of doing that, which is not very good. This should be HSO3 minus, is H2PO4 -1? Yes. Okay, so other than that, did you want me to still do it? You're good now? Okay, yeah, that's, I need to fix that.
Wait, so it's HSO3.
It should be HSO3 minus, not HSO3 2 minus. Yes. E? Yeah. Okay, so water is amphiprotic. It's the weakest acid, it's the weakest base, it's amphiprotic. Yeah? NH3, what is NH3? It's ammonia. Is it an acid or a base? Is it strong? Is it weak? It is a base. Is it a strong base or a weak base?
Doesn't matter if it's water.
It doesn't, because as long as you know it's not an acid, you're good to go. Although it will matter in terms of whether you write an equilibrium arrow or a two-way arrow, or a one-way arrow, sorry. Yeah? If NH3 were a strong base, you would write a one-way arrow. It isn't. It is Is NH3 a strong base? No. It is where is it over here? Is it a weak acid?
Oh, NH3?
NH3.
NH3 is a weak acid.
No.
Acid.
It is too weak to be an acid. It is the conjugate acid of NH2, but it is too weak to be an acid. You need to go and look for NH3 over here. Okay? NH3 is a weak base.
So like when it reacts with water, it's gonna act as a base.
It's going to act as a base.
You also look at anyone say that the NH3 is beneath the water, like on the acid side.
Yeah, you could. Where did it go? Did you want me to do the rest of it?
No, it's like I'll go back to the table. I like go down. Yeah, like you just say like that's the H2O's above like the stronger acid.
Yeah, you could, although that does, sort of ignore the fact that NH3 cannot be an acid,
So it's just like,
because this arrow does not go this way, right? Yeah.
But then the products would be NH4 plus, right?
Yes.
It would give away.
So this guy would give its proton
Right.
to H2O, so you would end up with hang on.
Huh? Is it-
Hang on. I'm doing it backwards. Miss Spence is wrong. No. Why did I erase the H? The H was the only part that was okay. So this one acts as an acid. And so the H goes this way. So we end up with OH minus plus NH4 plus. Yes. Any other questions?
So then,
Mhm.
so then for E, so you're looking at NH3 and then the other based on the product side to see which one it would favor, right?
Yeah.
Like, yeah.
Yeah, so you would either compare OH minus with NH3, the bases, or you could compare the acids. It'll work out the same either way.
Okay, so for OH minus and NHB, you never really look at it as like an acid because it's too weak.
Because neither of them act as acids.
Okay.
Yeah. Tony, you had another question.
I think I'm biting acid store.
That's okay.
But how do you like? Why is it that like if one's weak phase on the same side as the other is a weak acid? Like why is it weak, strong?
Because if this guy is the stronger acid, yes? Whoa, where'd it go? Sometimes it jumps on me and I just don't get it. I don't even know what happened. Where did it go? Okay, there we are. Whew. All right. If this is the stronger of the two acids, then its conjugate base, the stronger the acid, yes? Okay. So that means that this is the weaker the acid, the stronger its conjugate base, which means that you have the stronger and the stronger and the weaker and the weaker, and that's always going to be true. Yeah. I did an example with block 3 yesterday that was kind of interesting, actually, because it kind of took into consideration some of the KEQ stuff we'd been doing in the AP. So we had, let's just grab a couple of acids. We've got, let's say we've got HF plus CN minus, and that's in equilibrium with F minus plus HCN. Now, you could, this is our overall reaction. We could make this reaction out of the following two reactions. We could have HF in equilibrium with H plus F minus, yes? And reaction 2 would be HCN in equilibrium with H plus CN minus. Now, how could we have these two reactions add up to give us the overall reaction? What would we have to do? So this one proceeds in the direction, because we've got HF in the reactants, we've got F minus in the products. So the K for this, the Ka for HF is 3.5 times 10 to the minus 4. Now the Ka for this reaction is HCN, 4.9 times 10 to the minus 10. However, if I add up these two reactions as is, will they give me the overall reaction? No. What do I have to do with reaction 2? I have to reverse it. I have to flip it. So we're going to flip this. And when we flip it, what happens to our K value? Yeah, it's going to be 1 over, right? So this is K of this one here. And that's going to be 1 over 4.9 times 10 to the minus 10. Are we good?
Wait, could you go a little bit up?
Because I want to have my CN in my reactants, and I want to have my HCN in my products. So what I'm going to be doing is I'm going to be, let's call this one 2 prime, because we've now manipulated it, yes? So we're going to add reaction 1 with reaction 2 flipped. Yes, and I'm going to rewrite them so it doesn't look as confusing. So now I have reaction 1, HF, in equilibrium with H plus F minus, and I'm going to write reaction 2 prime, which is going to be H plus CN minus in equilibrium with HCN, and its K value is equal to the reverse of the Ka, which is going to be 1 divided by 4.9 e negative 10 equals 0.9 e negative 10 equals 1 over x. So I get 2.04 times 10 to the 2, 4, 6, 8, 9. Okay, so I get 2.04 times 10 to the 9. Yes? And this guy here, its K value was 3.5 times 10 to the minus 4. Yeah. And so now if we add these two reactions up, do we add the Ks when we add reactions? That's the question. Chat with your neighbor about that.
Yeah, exactly. Wait, this one, so this would be similar to like the ionic? Because you're canceling.
It's like when we were doing the KEQ and we combined two reactions. How do we get the K of the overall reaction when we combine two reactions? We multiply. So this is K1 and this is K2 prime. So we're going to take K overall is equal to K1 times K2 prime, which is going to be 3.5 times 10 to the minus 4 times, well, this is why we're doing this, right? Because, you know, the more times you see things, the more likely you are to remember it, right? And we get 7.14 times 10 to the 245. So K overall is greater than 1, therefore the products are favored. So if somebody asks you to prove it doing some math, like say on an AP exam, I will never ask you to do that on a regular exam, okay? But if someone asked you on an AP exam to prove it, you would do it by using that manipulating K kind of stuff, yeah?
So this is not going to be on the quiz?
This is not on the quiz, no. Okay, because for you, all you would have to do is you would have to say, this is a stronger weak acid, this is the weaker weak acid, which means that both weaker things are always on the same side, right? Both stronger things are always on the same side, and we always favor the weaker side, and our products are favored, and we didn't have to do any math. That's it. That's as far as it goes. Yes, Taranya. I did not. It should be 2 sig figs at the end, but because I was just looking to see if it was bigger than 1, I didn't really care. What? What? You mean, did I keep my whole number? Oh, I kept my whole number. It was in my calculator the whole time. I didn't write down everything because it's in here. Yeah? So I get 7.14285.7143 is what I really get.
How you would prove it.
So this is how you could prove it mathematically. If somebody asked you to justify your answer using calculations.
That can happen.
Hi. Sure, we're doing nothing exciting today, but yes, you may. Okay. Is everyone okay having their picture taken?
Yeah.
No? Okay, don't take her picture. Just maybe back of the head, okay? Okay. All right. So, that's it for that. We good? Any other questions from the homework? No? Okay, very good. So we were last day looking at strong and weak electrolytes. We were on page 55. And before we go on with this, I would like you to distinguish between, for your partner, distinguish between strong and concentrated, and distinguish between weak and dilute. Explain the difference to your partner.
Either way. No, but
They're highly scientific hot plate, which is keeping them warm. Okay.
but that means like. Yeah. Partially. That's why.
What is the difference? Strong and concentrated. What do we got?
So for dilute, a species
For dilute, a species.
reacts with water, but doesn't dissociate 100%. While the strong and concentrated, they dissociate.
Oh no, sorry, I'll clarify. I want you to do two tasks. Number one, distinguish between strong and concentrated. What's the difference between those two? Task number two, distinguish between weak and dilute. What's the difference between those two? I'm going to give everyone a minute and then I'll talk to you, Tony, okay? Yeah. Okay, sorry I wasn't perfectly clear on that. I'm going to go to Tony first because he had his hand up first, but then I'll come to you, okay? Yeah.
Yeah.
Okay, Tony, go for it.
Okay, so the difference between strong and concentrated is that when it says something is strong, it usually automatically dissolution, and when something is concentrated, it just is alive forever.
Yeah.
A lot of water. Oh.
Okay, so strong completely ionizes. Concentration has a lot of solute. Juno, would you like to do the second part for us? Yeah. Dissociates partly and dilutes, sorry? Yeah, not a lot of solute. So are we good with those distinctions? Okay. So back here, an acid is a substance that forms aqueous solutions with a pH less than 7. Acids ionize or they dissociate to form H+. Now, our strong acids, you know that there are how many? 6. Without looking, see if you can name them to your partner.
Wait. Yeah. It would be a minus.
Okay, but someone might do something, some you didn't.
Right. All four.
Wait.
Yeah, because if you look for it, actually we don't have it. Oh, I don't.
I just thought of a good mnemonic for the always soluble ones.
Always soluble?
Yeah, because I'm going to do that after this because we're in the process of memorizing something.
No, this is strong acids.
So I have them in the order here of Chloe, Cly, Burr, Son. Okay. But you can also remember, so I brought no clean clothes. Okay. SO4, I, Br, NO3, chlorine, and ClO4. Is it ClO4? Yeah, okay. Now, because we're memorizing things, can you remember the three things that are all three ions that are always, or the three categories of ions that are always soluble?
Alkaline metals, alkaline earth metal,
Alkali metals?
alkaline earth metal.
Nope.
No.
Nitrate.
Oh, wasn't it except for like two of them?
Nitrate.
Oh, nitrate.
Who's the other one? Ammonium. Now, what I just thought of is you've got Al, Am, NO3, which sounds like LMNOP. LMNO3. LMNO3. LMNOP.
And you just strip the piece of this.
And you just put a P, you 3 instead of a P. LMNO3. 3. LMNO3. Alkali. Just don't think it's aluminum, okay? But you guys know aluminum's not like a soluble thing, I hope. Fingers crossed. Alkali metals, ammonium, and NO3. That just made me really happy. I'm like, Am. Yeah, anyway. Okay, so those are our strong acids, and what they look like in water is they look like this. Yes, all ions all the time. And then we have our weak acid, which is only partially dissociated. Look at that. Very few ions comparatively. Okay, carrying on. Don't confuse strength with concentration. Strength is how much an acid dissociates. Concentration is how much acid there is in a certain volume. So concentration has to do with molarity. So here is a solution that is both strong and concentrated. Look at that. Strong and concentrated. Lots of ions everywhere. Here's an acid that is weak and concentrated. And if we look at how many ions we get, it's not very many compared with all of these ions. So many ions, so many. Yes? We can have a strong acid that is dilute. And if we have a strong acid that is dilute, you'll probably still end up with like a medium conductivity or low if it's super dilute. Huh? So if we look at all our ions here, 1, 2, 3, 4, 5, 6, 7, 8, that's still more than our weak acid when it is concentrated. You would have to dilute that acid, strong acid, even more to get it down to the same concentration of ions. Okay, and if we have a weak acid that is dilute, conductivity is very low because there's very few ions. Is this all making sense? The kind of question that could come up is, how could, you've got a weak acid and you've got a strong acid, and they're both, like when you put a conductivity apparatus, do you guys know what a conductivity apparatus is? Sort of. Let me grab one. We remember this thing? Yes. Yes. You don't remember this? Okay, so basically what we have here is we have two wires, which I can touch right now because it's not plugged in. And if we have a conductive solution and we put it in there, then the light bulbs will light up, okay? It will show different degrees of brightness based on whether it is a strong electrolyte, lots of ions, or a weak electrolyte with not as many ions, okay? So I'm going to plug this guy in. And now I get scared. One time I accidentally touched the two wires, and that was not fun. Not with this one, it was a different setup. Not go in. Well, okay, and we need to make sure this is on. And then I'm going to turn it off because I don't actually want it on yet. And I'm just going to grab some solutions. Okay, so we have uh, 1 molar acetic acid. We have 0.1 molar HCl. We have 0.1 molar acetic acid. And what have I got? Where's my other HCl? 1 molar HCl. Okay, so I have strong acid, concentrated. I have weak acid, not concentrated. 1.0 molar HCl. I got 0.1 molar HCl. I got 1 molar acetic acid and 0.1 molar acetic acid.
Miss Spence,
Yes.
Dorothy had a question.
Yes.
So if you have like a really, really concentrated strong acid, like what potential blow up?
I don't know. I'm not willing to test it out though because it's really hard to get a hold of incandescent bulbs these days.
Yeah.
So, like I said, I'm not really willing to test that theory.
But would it?
I don't know. I don't know. Ask your physics teacher. They know me about resistance and things like that.
What have you asked? You have that sense. You're closer.
Okay. So let us try our 1 molar HCl. Okay. This is our 1 molar HCl.
Oh, it's like a little yellow.
And I want some water. I don't know why it's yellow. We'll just ignore that. It's not supposed to be yellow. It's probably just like from the plastic. That'd be my guess. Now, first of all, I got some water here, just plain water, because I'll want it for rinsing and stuff. Is it going to light up with the water?
Now.
Let's see. No. Okay, super exciting that was. So now let's try our 1 molar HCl.
Whoa.
Yes? Nice, right?
That's right.
Now let's do our 1 molar weak acid. Or should we do our 0.1 molar weak acid or strong acid? Let's do our let's do 1/10 the concentration, okay, of our strong acid.
Like less bright?
It's still really bright, right? So that's 10 times less concentrated. Okay.
I think that one.
Now let's try our 1 molar weak acid.
I'm going to find it.
1 molar weak acid. Yeah. So this is 10 times more concentrated than the strong acid we had a minute ago. And yet it is barely managing to get those bulbs lit. Okay. And now let us try 0.1 molar of the acetic acid.
Miss Bench, what's the point of 3 light bulbs?
It just shows you, like, I don't know. There's always been 3 light bulbs. I think sometimes, like, if it's the brightest one, it'll actually light up the 4th one up here.
That's
Yeah, it's like a little LED, I think. I don't know. Is it a little light bulb or is it a little LED? Oh, that's a real actual, it's got a filament in it. So it's not an LED, I don't think. I could be wrong. I don't know. Like a little mini bulb. Okay, 0.1 molar acetic acid.
Nothing.
Oh, okay. Yeah, can you see the bottom one is just barely glowing? Okay, it kind of takes a while. There we go. All right. Now, shall we see how much we have to dilute our HCl by to get it down to the same as the 1 molar acetic acid? Let's do our 1 molar acetic acid for reference. This is our 1 molar weak acid. Okay. And this will do. Actually, what am I doing? Okay, so let's take some of our 0.1 molar and let's put about 10 mils in here. And if I want to dilute it 10 times and I've got 10 mils, what should my final volume be? 100. And I'm just ballparking this, okay? We're not being super fancy in our measurements. You would never use a what you call it? A beaker for measuring anything, really. Okay. So this is 0.01 molar. HCl. Which one was it? I think it was this one. Yes, that one. Okay. Still brighter, right? Still brighter than our acetic acid. Okay, we're going to dilute once again. So I'm going to put 10 milliliters in here. Okay. Oops. Okay, so 10 milliliters of this. I'm going to go in here. And we're going to dilute that again to 100. Okay. So now we're at 0.0001 molar HCl. Let's give that a go. Oh. Did we go too far? Okay, let's try that again. Let's try a 1 and 2. Okay, so we're going to take 20 milliliters and dilute that to 40. Close enough. All right, so this is now half of that, so that's going to be 0.005 molar. I have too many beakers now, I don't know what's what. Still a little bit too high, yeah? So let's try a 1 and 3. Right, it's going to be somewhere in there. I'm not going to spend all day trying to find it, but do you see how it has to get quite diluted to get down to the same, right, as the 1 molar? Because we're down to like almost 1,000 times diluted. Okay, cool. Wow. And that is a conductivity apparatus, and you should know that that's what it is called, and you can use it to test for conductivity. Shocking. Okay. I'm just going to put all of these back before I forget to do that. Strong acids are considered strong electrolytes. Weak acids are considered weak electrolytes. No one is ever going to ask you something stupid like if you ask you if a dilute strong acid is a strong electrolyte, that's just a semantics game. So no one's going to ask you that. Okay, does that make sense? Okay. Strong bases. Who are most of our strong bases? Alkali, metal, high. Hydroxides, yes. Okay, most of our strong bases are our alkali metal hydroxides. What type of bases are those? Metal hydroxides, what type of bases are those? They're strong. What definition do they fit under? Arrhenius. Okay, so you have your two strong Bronsted-Lowry bases, the NH2 and the O2. You also have the soluble metal hydroxides. So I don't think you need to memorize these ones. Calcium hydroxide, they call it soluble. It's not that soluble, nor is strontium, nor is barium. On your solubility table in your book, it says that only out of those 3 alkaline earth metals, only Strontium hydroxide is considered soluble. So just go with whatever they tell you on the AP exam. You're not expected to memorize any solubility rules other than LMNO3. Okay. Strong bases dissociate completely in water. Li, OH gives Li and OH. CaOH2 gives Ca2 plus and 2OH minus. The abundance of free-floating ions mean they are excellent conductors of electricity. You should also, because you are brilliant people, be able to tell the difference between a base and an alcohol. They both contain OH. A base is going to have a metal or NH4 plus or ammonium. But you're going to have an ionic bond. And if you've got an ionic bond with your OH, your hydroxide, then you have a base. Okay, so ionic bond, hydroxide ion, that is a base. If you have a covalent bond and you have a hydroxyl group, then that is an alcohol. Not a base, the OH does not come off. You need an ionic bond for that OH to come off in solution. So, how do these things work? Our bases dissociate as long as they are soluble. Okay, so you can see them coming apart. We got NaOH gives Na plus and OH minus. BaOH2 gives Ba2 plus and 2OH minus. CSOH, cesium hydroxide, gives Cs plus and OH minus. Those are your bases. They all are metals with hydroxides. Alcohols, usually you're going to have carbons because alcohols are a type of what compound? Organic. Okay, alcohols are organic compounds. And organic compounds are based upon carbon chains, yes? So you might have CH3OH. That's a liquid. If you dissolve it in water, it disperses. It does not dissociate. Yes? Does that make sense? So what do I mean disperse? Okay. Dissociate. Yes? Dissociate. Disperse. Yes. Dispersal just means the particles separate from one another. Okay?
Associated with like a particle.
It's when the ions separate. Okay? And dispersal is when molecules move apart from one another.
Particles?
What?
Is it okay if we say particles?
Particles? Yeah, although this is ions, and ions are also particles.
Okay.
Molecular compounds are the ones that disperse. So like sugar, you take sugar and you dissolve it in water. Each molecule is still a sugar molecule. It has not split apart into different atoms or groups of atoms. It's still an intact sugar molecule. Okay? Okay, so all you're doing when you have an alcohol going into water, the only thing that changes is the, whoops, that was supposed to be a highlighter. The only thing that changes is the state. So you should be able to recognize that bases are electrolytes because they have ions. Why is that not writing? So bases are electrolytes due to mobile ions. Are alcohols electrolytes?
No.
No. Alcohols, no ions. Non-electrolytes. I wish I'd left more space, but that's okay. I probably have something about this on the next page anyway. Let's see if I do. Oh, no. Weak bases. Weak bases are weak electrolytes, just like weak acids are weak electrolytes. Yes? What? What? Weak acids are weak electrolytes. Why are they weak electrolytes? They don't dissociate very much, so you get only a small number of ions, comparatively speaking. Weak bases are also weak electrolytes. And weak bases, these are what type of bases? All of your weak bases are what type of bases? Bronsted-Lowry. They are not compounds of hydroxides. They do not contain OH minus.
So is it impossible for like acid to be both? Yes,
For an acid? Okay, so bases are usually one or the other. Yes? But acids are like either you're like, oh, it just separates into H and whatever the ion is, Cl, or it donates to water and it's H3O plus and Cl minus. La la. Okay? Yeah. So acids really don't care so much. I mean, honestly, again, this is all a bit of a semantics game, so don't get too wound up about it, right? But yeah. Semantics means words, wordplay, like just mucking about with words. Yeah. Because sometimes it's often used in the case of, if somebody's making some sort of argument and really all they're arguing over is like definitions of words. And if they could come to some sort of agreement on what the words actually mean, then you would not like have an argument anymore. That's usually like, it's just a semantic argument and it's often not worthwhile, right? Because it's just about what are we defining things as in a particular moment. All right, so here is NH3. What type of substance is NH3? NH3 is a acid or base? It's a base. Is it strong or is it weak? I got both. Convince your partner. Is it strong or is it weak? It is weak. Its conjugate base is a strong base. Yeah? Okay, so it's a base, it's a weak base. And we have water, which is amphiprotic, but because it's with a weak base, it's going to act as the acid. And it's going to give its proton, H+, to the NH3. The H is going to tack on to this lone pair right here. And that bond is going to form there. So we end up with NH4+ and OH-, and that's where our OH came from. Yes? This equilibrium is a process that lies heavily to the reactant side, meaning very few ions on the right-hand side. So here's just a picture showing you a strong electrolyte with the bulb being very bright, a weak electrolyte with the bulb being not as bright, and a non-electrolyte where we have no light bulb lighting. Which one is a strong base? Are we okay? Brian, yes.
So for like when it's like hydroxide and like, for example,
Beryllium and magnesium, those are non-soluble. They're low solubility.
are these still bases?
They will give you a basic solution, but it's going to be very, very tiny. So for example, let's go just take a quick look at our data booklet, if it'll let me do that. So for example, magnesium hydroxide has a KSP, which is the dissociation constant, okay, Mg2 plus 2OH minus, of 5.6 times 10 to the minus 12. Yeah? And in unit 3, we will be able to figure out, you know, what the concentration of hydroxide is based upon that. Okay? And in fact, what you would get is you would get X and you would get 2X. And so the K would be equal to Mg times OH squared, right? So that would be X times 2X squared, which is going to be 4X cubed, which is going to be 5.6 times 10 to the minus 12. So X then is going to be equal to 5.6 E negative 12 divided by 4 equals cube root. Where's my cube root on this calculator? There it is. 1.1 times 10 to the minus 4. And so concentration of hydroxide would be 2.2. Yeah, which is quite a small concentration. But we find it using the solubility K value rather than a KB. Yeah? Okay.
There is still a ground support.
It would be an Arrhenius base. A very, very weak Arrhenius base. But, yeah. But we don't have Ks for Arrhenius bases, so there we are. All right. We're almost out of time, aren't we? I think so. Oh, and look, that leaves you with pages 59 and then, yeah. So page 59 and then anything you haven't done in pages 60 to 64. Have you done all of 60 to 64? No. 59 and 60 to 64. Okay, and we'll talk about the leveling effect tomorrow. Leveling effect. It's only one page.
What's a leveling effect?
The leveling effect says that there is no stronger acid that can exist in water than the hydronium ion. And the reason is that anything that is stronger than the hydronium ion is actually a strong acid. And the moment you put it into water, it donates its protons to water and becomes the hydronium ion.
So is it like dairy?
I don't know. It's just a thing.
Just a thing.
Basically, the conjugate acid of the solvent, like, so if we had a different solvent than water, it would be the strongest acid that could exist in that solution. So if ammonia were our solvent, its conjugate acid, NH4 plus, would be the strongest acid that can exist in ammonia.
Okay.
But in water,
Uh-huh.
the strongest thing that can acid that can exist in water is H3O plus. Yeah. There's more to it than that, but I never really grasped the more to it than that. So, and you don't need to know anything more than that, so we're going to just leave it there. Today is Tuesday, right?
Yes.
Oh, and it's 19, not 16, but that's okay. We finished perfectly. Yeah, I think we're good. Yeah.
All right, go quick.